Hi, we're back. I hope the previous sessions were informative. We're going to conclude this particular analysis or design of the enrollment system. We're going to dive a little deeper into how the software architect puts together an application. And again, we're only at the beginning of this. This is just what you do at the beginning when you're trying to establish the application vocabulary. We're going to look at a further drill down into what that application vocabulary is for the enrollment system. And we're going to introduce the use of design patterns, which are ways of reusing thinking in the same way that software libraries are ways of reusing code. So we'll continue. We left off with the what's called a conceptual class diagram. It's a UML artifact that shows an overall layout of the way different objects uh, that support the application interconnect. So let's look in particular at what those relationships are. There's four of them. When you look at the diagram, you see one college has n departments. N departments belong to one college. That's a one-to-one relationship. There are relationships like one-to-one where the teacher has a schedule. One teacher has one schedule. The rest of them, for the most part, are one-to-n. So let's look at what that really means. If you're defining, and these examples are going to be C++, which is the bad news, but the good news, they're about 2 lines long, so they should be interpretable. Um, a one-to-one relationship. Class teacher has a schedule, and that's it. It's one teacher, one schedule. One to n, excuse me, is every teacher can teach many sections, but a section only has one teacher. So from the teacher's point of view, it's a collection. In this particular case, it's a collection of 20 section pointers. So one to n involves a collection. The one collects the n. N to one is the reverse. If you have n teachers belonging to a given department, each teacher has a pointer back to the department. So a department has a collection of teachers, that's one to n, and teachers have a single department, that's a pointer back. That's the n to one relationship. And then you come to the fourth one, which is usually a problem, and that's n to n. A student may be enrolled in many sections, but every section can have many students. So that's an end to end relationship. And those are tricky. Let's take a look why. So we have a student taking n sections, section being taken by n students. How do we implement this? How do you implement an end to end relationship? Well, you might try two separate pointer arrays. So a student has an array of pointers, one to each section. Section has an array of pointers, one to each student. And this might work, except for the fact that it has its own data. So a student in a section has final grade, attendance records, exam grades, teachers' comments. Those are all specific to one student in one section. And the question is, where is this info stored? If a student has pointers to a section has pointers to a student, there's no place to store the data that uniquely binds that student to the section. In general, an end-to-end relationship with data associated with it is usually a design error. So what do? You use a design pattern. And the design pattern that we're going to use in this particular instance is the junction class. A design pattern is known to software architects, and this is one of the common design patterns that is used in dealing with this particular type of architectural problem. So you create in the middle between student and section, you create a thing. And that thing, a student collects n of them, and a section collects n of them. And That thing contains the final grade, the attendance records, all of the all of the information that was at that junction between student and section, and it contains a pointer back, being a one to n, being an n1 relationship with student and section. It contains pointers to both of them. So if I was the student and I wanted to find out all the sections that I took and what my grades were, I would go and look at each thing that I collected, and that thing would have the grade and would have a pointer to the section so I could get it. And likewise, if I was the section and I wanted to find out all the students in that section, I would go to my collection of things and ask the thing, give me your student. And I could walk through the list of students and I would be able to get at the information stored in one place about how that student did in that section. The question is, what is his thing? I mean, is it a schedule? Is it a transcript, roster, registration? Some of those, none of those actually fit. A student schedule is something totally different. A transcript is the collection of grades that a student got. It's not one specific grade for a section. It's not the roster. A roster is a collection of students within a section. It's not one student in a section. So we have the concept of the thing. We just don't know what the thing is. So we start thinking, because we're software architects, we think, what binds one student to one section? Well, a student has multiple things. A section is allocated with, in the case of typical section at the Anza, 55 things. It has room for 55 students, 15 of them waitlisted. A thing is either valid or invalid, whether there's a student there or not, and it contains grade, attendance records, and so on. Calling it an enrollment, you could say, okay, a student has 5 enrollments, one in each section. A section has 50 enrollments, each one by a student. It kind of fits, but if in thinking about it, turns out we can do better. Call it a seat. And the moment we call it a seat, everything clicks. The registrar knows what a seat is. A student has multiple seats, one in each section. A section is allocated with room for 55 seats, some of which can be occupied, some of which are empty. We use the word seat as the thing that binds a student to a section, but notice it's not seat like you define in an airline, where the seat would have a unique ID like seat 44A, and have a unique cost and have an assigned student. A student sits in a seat, but a seat is in the enrollment application is an abstraction. It's not a physical reality. At the moment that you define the word seat to be the thing that joins student to section, everything makes sense. A student occupies n seats, a section contains n seats, and a seat has all of the information about grade, attendance record, and so on. So we've added seat. And at this point, we are starting to really get a handle on what are the refined abstractions in the enrollment system, starting with the functional specification and then doing some staring at the ceiling and coming up with the first really UML artifact, which is the conceptual class diagram, that's going to define the way the abstractions that we've identified relate, and it's going to define the meaning of these words within the application. So this is what the enrollment system specification looks like at the Anza after the software architect has corrected it. So notice the highlighted words. First paragraph is pretty much the same. Second paragraph, each course is instantiated by one or more sections. That's important. That's a requirement that the registrar would agree with, and it's a requirement that the programmers can actually implement. So the architect, again, is bridging between what the domain expert is trying to define and between what the programmers understand that they have to do. We've added each section is assigned a section number and has a schedule which defines the set of times that it meets. We've talked about teacher and room. We knew that from the beginning. Students may then enroll in a section if they are paid up, have taken all its required prereqs. So we understand that prereq is now a part of the functional specification. And then at the bottom, if the student is accepted, she will be assigned a seat. Her attendance will be tracked. And at the end of the academic quarter, she will receive a final grade. So we've taken the functional specification and we've added to it the things that we needed to do to make that specification real and implementable. And all of this is heading toward defining a common application-specific vocabulary. The software architect is bridging the gap between the domain expert and the programmer. One simple way to do this is, and again, this is just a very simple first pass attempt to define an application vocabulary. If it's a noun, it's a class or an abstraction. If it's a verb, it's a method or a function or a subroutine on that class. If it's an adjective, it's a type. So let's see, virtual section. Well, let's look at an example. A foreign student enrolls in a virtual section. We're going to parse that sentence. This is something that the registrar might say. And in terms of parsing that sentence, we now understand what that sentence means to the abstractions that we've defined. Student is a class. Foreign is a type of student. It might be a child class of that student, or it might just be type of that student class. Section is a class. Those are nouns. Virtual is a type of a section. I have a virtual section. I have an on-campus section. Enroll is a public method. So a student enrolls in a section or a section enrolls a student, but we understand that enroll is going to be a method that we're going to have to support in one of those two objects. And so when we hear words about the application, we're able to map that to the definitions of the classes, of the types of classes, and of the events or the methods that they have to support. That's what we're trying to do, to take that functional specification and make it into something that can be implemented. I wanted to talk for a minute about design patterns. Design patterns, as we said, we looked at one, the junction set. It took a problem that we had, which was an end-to-end relationship that had its own data. And when an architect encounters something like that in the design, where you go, I have this problem and I don't quite know how to model it, typically what the architect wants to think of is, am I the first architect who ever before ran into this problem? Am I the first one to ever encounter this? And if the chances are no, you're not, then you start hunting for a design pattern. How do I reuse the thinking of those architects that have gone before me? Again, in the same way that a software developer would look for an object library solution to, say, schedule. What do I want to write the schedule object when it's probably been written already? So design patterns formally document these designs so that they can be reused. And the classic book on design patterns, the thing that created it, is the URL is shown here. This is a PDF file. It's free. It's on the web and it can be downloaded. It is design patterns. The four authors are called the Gang of Four. That's not to be confused with the people that took over after Mao died in China. This Gang of Four gave us design patterns. And it's worthwhile looking at. As a software architect, you don't have to know all the design patterns in that book, but you do really want to get familiar with the index to the book. So you can look through the index and say, is there something in here that can meet the challenge that I'm facing in this design. So here's a challenge: policy customization. Um, we have an enrollment system. We've architected it, designed it, and implemented it, and it is running at the Anza College. And we want to sell it to other community colleges. We want to sell it to other um, other training institutions, perhaps corporate training institutions. We want to be able to resell it, but we have a problem. There's a lot of policy hardwired into the application. Policy is things that define how an application works at a given site. So, what's the maximum number of credits a student can take in a given term? Maximum number of office hours, minimum number of enrolled students below which the section gets canceled. These are numbers that are part of the application, but they're going to vary with every place that application is installed. So if we're a customer, how do we avoid minimizing the recoding that's involved when we sell it to a new college? Um, where do we make those changes? We certainly don't want to make them in the code itself, because if we make the changes in the code, that means every new site we sell to has to be recompiled. Um, and that is a nightmare, because it means that we need a separate code tree for each customer that we have, which has their policy constants in. And when we did a fix, we'd have to put it in all those code trees. When we did an enhancement, we'd have to put it in all those code trees. What we really want is one code tree, and to somehow take out of the code all of these specific policy values that would otherwise be in the code. It has been said, and I'm a believer in it, that the only numbers you ever should see in code are 0 and 1. And if there are any other numbers in the code, it's the page number of the code listing that you're looking at. So how do we get it out of there? And at this point, we might think, well, I couldn't be the first software architect to have to try to figure out how to remove the impact of the various policy values on a given site. So this is the fixed property design pattern. This is the one that we'll use to solve this. And this is how design patterns are defined. There's name, classification, intent, minimize changes by encapsulating site policies. When do you use it? When you use it when business constants are site specific, and that they change on a regular basis. The implementation, you have when in doubt, encapsulate. So we know we've got a problem with taking all those constants out of all of the places that they are in the software. And so what we immediately think of as an architect is, what if we had a solution? Let's define a solution. Let's make it into an object, and let's try to figure out what the interface looks like to that object. When we do that, we realize, well, if we had an object that you would give a key, you'd say, what's the value of this? And you get back a value. That'd be great. I have no idea how I'm going to do that, but I know that if I'm going to do that, that would be the object that would help me pull all of those numbers out of the code. This object would know the numbers. You could ask it, what's the value of this? And you get back the value of that particular parameter at that particular site. It would be different per site, but the code that asked for the value would be identical. It's just this fixed property design pattern object that would be different, or maybe not. You'd have to look a little further. So here is how we encapsulate site policy. We have key, which is the string that defines the policy. And this would be for a library, for example. Maximum number of days a book is on loan, fines per day, how many months does a library card go before it expires? What's a site license? All of those, we define all of the parameters, and then that's the key. And we ask the site policy object, hey, for this particular site, what's the maximum number of days on loan, or how many credits can a student take if it's the enrollment system, or whatever the parameter is. The site policy object uses a hash table. And again, I'm not going to get into what a hash table is, but it is a data structure that if you give it a key, it immediately returns a value. And in this particular case, we're looking at a library system, and or whatever the name of the application is. Any object in that application relying on a site-specific policy may get the value by going to the site policy object. No code needs to change when the application is run at a new site. Now, the point I wanted to make before I get into the last slide is how does the site policy object do it? And there are several ways that it can do it. The first way is to just, when you ship your code to a given site, you have a table, there's a file, it's called a configuration file. And the site policy object is the only object in your application that knows where that file is and knows to go there and get the values of those policy fields for that particular site. And that solves it. The only thing that's specific to the site is the installation file. The code is identical, which means you can have one code tree, and when you make a fix, you put it in once, and when you make an enhancement, you put it in once, and all of the site policies are defined in an individual file that you send out to the customer. You can do better than that. If you have every site that you sell to has a site license, the policy object can make a request over the internet and say, what is the value of this particular thing for site license X31PJJ6? And it can get it back from your headquarters. So if we have a company and we're selling this to 15 different customers, in this particular case, we're always involved with support. We know that they're using the application. We're in communication with them. If they say we want to make a change, they don't have to make it. They just let us know what it is. We make the change. And the next time the site policy object says, what's the value of, number of courses a student can take, it goes upstream and it says, I'm site license, whatever, what's that value? We return that value, and it then returns it to the application object that was asking for the value. The point being that you can have an installation script where you can go upstream to the corporate headquarters to get the value. The only one that knows you're doing that is the site policy object. None of the other objects in your application has to know or worry about it. And that is a typical use of a design pattern. To be able to solve a problem that you have using previous thinking of the software architects that have gone before you. Until design patterns came along, science advanced. One generation would stand on the shoulders of the preceding generation. In software architecture, it was one generation would stand on the feet of the preceding generation. You never got up very high, and you were always tripping and falling over each other. With design patterns, we are also at the stand on the shoulders level. You get to reuse that thinking. So the question, you've seen a little bit about how software architecture works, what the software architect does when they stare at the ceiling and then go out to lunch. In terms of making your career, even if you decide that you don't want to be a software architect, you're going to focus on the programming aspects of it. Knowing about design patterns makes you a better programmer. Knowing about software architecture makes you a better programmer, because you now understand more than the objects that you're doing. You understand where it fits into the overall system, and you understand how to go and talk to the customer and find out what they really want, which, if you're building an application, is always a strong thing. So in answer to the question, can you be a software architect? Let me refer back to a former president who I deeply miss. Can you architect a software application? You can do it. Yes, you can. Thank you.